Okay, good afternoon. Good afternoon, everybody. You're welcome to the seminar series for the month of March. And today we are going to I want to thank you for coming to participate in this seminar series. And you are welcome to the seminar series for month of March. And the title of today's topic will be given by Dr. Johnson Oyero. So, but before Dr. Johnson starts, I will call on Ms. Festa to read his biography, his bio sketch. Ms. Festa, over to you.
Okay, good afternoon, everyone. Can you hear me? Hello? Hello, good afternoon, everyone.
Yes, we
we
can hear
you.
you.
We can hear you. We can hear you.
Okay.
Afternoon. I hear you.
Okay, yeah. So I'll read the bio sketch now. Dr. Johnson Olubori Oyero received his Ph.D. from the Université Libre de Bruxelles, Belgium in December 2025. His research lies at the interface of computational fluid dynamics, nonlinear dynamics, and physical chemistry, with a focus on modeling heat and mass transfer in multi-phase and reactive fluid systems. His work investigates how chemical reactions, diffusion, and buoyancy interact to generate and control hydrodynamic instabilities and pattern formations in stratified fluids. Through mathematical modeling and high-resolution numerical simulations, his research aims to improve the prediction and control of mixing processes in environmental, industrial, and geophysical flows. He has presented his work at several international conferences and seminars. Thank you.
Presentation.
Good evening, everybody. Can you hear me?
Yeah.
Okay. So it's my pleasure to present my talk this afternoon. It's a multiphysics problem, and it's about instabilities that develop in fluids when they are stratified. We'll be looking at the role of chemistry and diffusion in this process. So first, I'm going to give her a kind of gentle introduction into fluid instabilities, or what is called hydrodynamic instabilities. Then we will look at the next part where we look only at the role of difference in diffusion, how it influences mixing and fluid instabilities. And the second part, which will be the closing part, we look at the role of chemistry. I hope you enjoy this talk. For a start, I begin with the word hydrodynamics. Hydrodynamics is a mixture or a combination of two words, hydro and dynamics, so which essentially means the dynamics of water. So it studies all the kind of motion, all the kind of movement that water can undergo when a force acts on it. For you to understand this, look at this cup of water, for example. According to Newton's law of motion, a body at rest will remain at rest unless acted upon by an external force. So this water is still, we do not observe any macroscopic motion. For the same cup of water, if you stir it with the water, you are going to share the fluid layers where the fluid closer to the surface are more stretched than the one at the top. So you have a sharing forcing induced by mechanical stirring. Another kind of hydrodynamics that can be observed is when you pour water from a height. Because of the gravitational force that acts upon everything on the earth, the water tends to fall down. Similarly, we can have, when you have your cup of water or your cup of favorite carbonated drink, you can see sometimes bubbles rising from the bottom of the cup to the top of the water. This is because buoyancy is acting. The less dense gases at the bottom seems to rise to the top. So if you are familiar with Archimedes' principle, and then if you have a pump, a pressure tank, because pressure varies with height, you can induce different degree of motion with pressure gradient. So this kind of give you an overview of what we say in a layman's language, in not a strict mathematical sense, in a layman's language, what we mean by hydrodynamics. And then that takes me to hydrodynamic instabilities. They are instabilities that develop when hydrodynamic is in motion. Of course, that seems straightforward. We have seen that mechanical action can cause motion, pressure can cause motion in fluids, but this kind of different motions can also trigger hydrodynamic instabilities. And there are different types of hydrodynamic instabilities that can be observed. And then to conceptualize this, I give you one of the popular one that is called the Rayleigh-Bénard instability. It is an instability that is observed in fluids when you heat the fluid. And what is an instability? An instability is is a change of state when a fluid is in a reference frame, initially stable, and because perturbations to it grow in time and space, then it becomes unstable. So this is your favorite pot on the heating surface. No heat is applied. You see that the pot is still, the water in it is still. But the moment you apply heat to the bottom, you will see this kind of cellular motion that is induced. What is happening here is that as you apply heat at the bottom, the water at the bottom expands. And because it expands, you have something that is less dense. You have something that is less dense. And then at the top, the water is initially cool, so which is denser. So the difference in temperature triggers difference in density, and then you see this. And this is what is responsible for circulation of air in a room, for example. The blue arrows looks, if you're in a room that is initially cool, and then you apply a heater at the source, the hot air rises to the top, and then the cooler air that is initially in the rooms tends to sink downwards. So this kind of create a circulation and makes instability to happen. And this kind of mechanism is also responsible for transport of minerals within the Earth's core. Another type of instability is what is called Rayleigh-Taylor instabilities, which was first studied by the guy Rayleigh, and then it was advanced by Taylor, and we call it Rayleigh-Taylor instability. For you to understand this is let's say a glass of wine, and then you put some grenadine on top. You know, there is a water inside there, but then you are adding something that is increasing density at the surface, at the top. So you have something that is denser on top of something that is less dense. Previously, we have seen change in density due to temperature difference in Rayleigh-Bénard instability. Here, the difference in density is triggered by change in concentration, change in mass. So the same thing happens when you put milk in your cup of tea. So you can see this kind of wiggling instabilities. So we have something that is denser, and density increases when concentration increases. And this is also responsible for explosion in the galaxy and for some inertial transport. Of course, this is still part of the introduction. And then we have looked at two setups. Now let's look at stratifications that is generic. We are not looking at coffee. We are just looking at something generic. So suppose you have a solution. In chemistry, a solution is a solvent plus a solute. That is, you put a solute, let's say a powder, you put it in water and you mix, so you have solution, different kind of solution. Can be salt solution, can be acid solution, base solution. Your cup of tea is a solution. Your soup is a solution. So you have a generic solution A, with concentration A and density rho A stratified over another solution B with density rho B. Based on the previous explanation that I give, in this stratification, if the density of what is the stratification on top is greater than this density of what you have below, then you are in what I have described as the Rayleigh-Taylor instability configuration. And when you do a cross-section of the profile, you have this kind of 1D profile where you have something that is denser, rho A equals to 1, and for illustration, rho B equals to 0.8. In the reverse case, if what is above is less dense, if what you have above is less dense than what you have below, then you can define a parameter R, which in this case is greater than 1. And for this configuration, the stratification is stable. And this means that we do not expect instabilities to set in. Why? Because there is no favorable gradient in density to trigger concentration. So, but in this kind of setting where the configuration is stable because of density stratification, there is another mechanism, which we will see now, that can destabilize this stable configuration. And that takes me to double diffusive instability. This configuration, where what you have below is denser than what you have above, is stable. But if, in addition, we are not just looking at the density difference, but we are looking at the species that are dissolved in the solvent diffuse at some rate, and they follow Fickian diffusion. That's what we'll be looking at in this discussion. And it happens that what you have below, the solutes in the solution below diffuses faster than the solutes in the solution above. We can then define a parameter, delta, which is greater than 1. Although the configuration is stable according to density stratification, the difference in diffusion rate of the solutes in the stratifications will trigger what you call double diffusive instability. And the signature of this kind of instability is that instead of monotonic density profile developing, then you have build up of extrema, that is maxima and minima in density profile. Initially, there is a density difference that we call delta rho naught, which is the difference in density difference at the beginning. But once you incorporate the contribution of diffusive effects, then the actual relevant density difference is this bigger density difference that is called delta rho m. I hope you are following me. Now, for you to appreciate this, what is happening is that the species are diffusing faster at the bottom and going, but that is creating a depletion region. So you have a minimum in density and an accumulation region at the top. So the A as B is leaving the bottom and diffusing towards the upper strata. A is filling those gaps that B leaves behind. And that's why you have extrema in the density profile. And this kind of double diffusive instability, you can see it in transport of salt in oceans and in magma chamber, and it's been observed in several experiments. In summary for this introductory part, I have introduced you to the concept of hydrodynamic instability, and in particular, I've emphasized interfacial instabilities, which are instabilities that develop at the interface of two fluids, which can happen if there is a difference in temperature, Rayleigh-Bernard configuration, if there is a difference in concentration, and then a difference in density, you have the Rayleigh-Taylor instability. And if the species diffuse at different rates, then you have the double diffusive instability. Why is it important, you may be wondering, to study this kind of system? One of the reasons why it's important to study this kind of system is that it helps us to mix two fluids. What does that mean? Look at this simulation, for example, which is what I've been trying to explain. We have a fluid A layered on top of B. Initially, they are diffusing into each other, which is the green region in the interface. And as time passes on, you see the deformation of the interface into finger-like patterns. And then the two fluids begin to interpenetrate into each other. What happens is that this fluid become to mix. And what does mixing means? It means concentration begins to be homogenized in space and time. This is useful because you just make your stratification. The only thing you put there is density difference because of the choice of the solution that are stratified, and the fluid mix by itself. As someone would say, this is an energy optimization problem. You are not putting something there. This is in contrast to what you do with your blender when you are cooking in your kitchen, for example. You need to turn the blender, and to turn the blender, you need electrical source to turn the blender to mix your a recipe, whatever you're doing. So this can be useful in cases where you are producing pharmaceutical products that when you share them, when you apply mechanical action to them, you can destroy the relevant constituents in them, among other applications. And even in CO2 sequestration, maybe if time permits, so that I don't stay too much in the introduction part. So these are some of the application, and this is pharmaceutical application, for example. And I know you must have seen in drugs the notice shake before use. Why do they say this? For example, if what you have is some emulsions. So if you let it sit on the table for some time, you can see that it separates into layers. So if you just drink what is at the top, then you are just drinking what may not heal your body. And then, so those are practical examples. Of course, there are different examples that we can use. So what do we want to answer? According to the topic is that we want to look at the role of diffusion and the role of chemistry in influencing, in controlling the mixing that we have, and how can we choose the parameters that help us to control the mixing, and also importantly, how can we do a priori that, okay, I want this degree of mixing. I want my mixing to start by 10 seconds. I want it to start, no, much more later. I want it to start by 1 hour after stratification. I want it to be this fast. What are the things that we have to control? So these are the scientific questions. And this takes me to the framework for discussing my research, which is chemohydrodynamic instability. So which summarizes the introduction again. You have concentration gradient, difference in concentration that triggers either a mobility profile, which is density, viscosity, permeability, and then trigger hydrodynamic instabilities, which induces hydrodynamic flow. And sometimes we will see that reaction, just like diffusion, can trigger instabilities in some framework. And in this case, it will be important for us to see how reaction influence things, change density profile, etc. We will get there. So I will first look at system 1, which I've shown you, solution A on top of solution B, and we'll look at what if solution A is less dense than B, what if they are equally dense, what if this is more dense, and we'll look at difference in density. And then system 2, we'll look at the situation where the solutions are reactive and they are producing a new product in situ that is on the go at the interface. They are synthesizing something. For example, from high school, if you do acid-base reaction, you produce salt, a salt solution and water, among other things that you can produce. So which is modeled by the second order reaction, A plus B gives C. And to study this physical problem, I think The mathematicians will be happy now. Then we have this system of partial differential equations that is based on the Navier-Stokes momentum equation coupled with transport equations for the concentration of species A, B, and C. And the system is solved under the assumption of incompressibility. The red letters are the parameters of the problem, which are the numbers that helps me to gauge which regime that I will be. And they are defined as this. R is the ratio of the solutar expansion coefficient, alpha, and O naught is the initial concentration that you have in your stratification. This diffusivity ratio, which I've introduced to you earlier, is the ratio of the diffusion coefficient of the stratified solution, and the Damkohler number helps us to gauge the relative importance of hydrodynamic transport to reactive transport we can define it based on the time scales involved. And then the Schmidt number, which gauges the momentum diffusivity to species diffusivity. The terms highlighted in red account for temporal evolution of the velocity and concentration. As the velocity is changing, the fluid becomes entrained and the concentration is advectively transported. So you have this highlighted term accounting for advection because of the action of diffusion and temporal evolution. And this highlighted term in purple are the reactive terms. And for the action of buoyancy, that is, you are in the gravitational field. So this accounts for the buoyancy force on the fluid. And like I said, we are solving this under the assumption of incompressibility. This essentially means that we are looking at solutions that behave more or less like water. We are not looking at gas that expands uncontrollably. We are not looking at combustion. So there is incompressibility there. Okay. For the first system, so we look at the non-reactive system, part 1. So that we take the reactive terms away. So no reaction. You have the Schmidt number, the delta parameter. And for this simple system, when there is no reaction, if my R is greater than 1, I think you've seen this before, my system is initially stable. I do not expect instability. On the other hand, if it's less than 1, it's the Rayleigh-Taylor instability, RT, that I've shown to you. And if delta is greater than 1, you can have double-diffusive mode. So if it's greater than 1, I remind you again that what is below is diffusing faster than the species at the top. But when delta is less than 1, what is below is diffusing slower than what you have at the top. For simplicity, we fix the Schmidt number at 1. Typically in real-life applications, you have the Schmidt number of chemical solutions around order of 100 and 1,000, but this may make the solution stiff. But we have solutions for that I will not present, but let's just keep it simple. So you've seen this that I introduced to you earlier, and this is the deformation of the interface because of the action of the diffusion. The fluid is diffusing into each other, and then you have A and B. And then when you do a cross-section, so you have your A, you have your B, and then the density profile, which is a linear combination as defined in this problem of concentration of fluid A and fluid B. So let's leave this. For the Rayleigh-Taylor problem, R less than 1, delta equals to 1. That is, there is no difference in diffusion rate. The only difference is that the two species have different densities. By just varying the values of R, we can see that we can already influence the mixing. If R is closer to the value of 0, we see that at time t equals to 1, 2, 5, the destabilization of the interface happens much more earlier, and then the homogenization is fast. But when R is closer to 1, which is more closer to the stable value, there will be destabilization at the end of the day, but it's more delayed. So for me, I'm happy that I can choose solution pairs based uh, on my goals to delay or to enhance mixing based on the density stratification alone. And for you to appreciate these qualitative results, we follow this mechanism where we define what we call the mixing length. And what is the mixing length? The mixing length tends to measure the degree of interpenetration of the fluids into each other. Much more early, we have diffusive mixing. So this grows as square root of time, which is classical and characteristic of Fickan diffusion. But much more later, when convective motion sets in, then we see a motion that grows as a quadratic function, the interpenetration of the fingers. So this is characteristic of free fall motion. If you remember your physics, this is characteristic of free fall motion when the distance h is equal to half gt squared, if you remember. But there are theories for this. And why do we measure? Based on this quantification, by following the evolution of the interface, we can already define the onset time, the time that the mixing transition from diffusive mixing to convective mixing. And we can also quantify the acceleration, how fast the fluid are going into each other by looking at the slope of this curve in the convective region. So these are our quantitative parameters. We've defined this density difference. Okay, and what we find is that there is indeed a correlation between the time that the instability sets in and the dynamic density difference. So this is a power law. So without doing the experiment, I've done the experiment. You just have to come to my results. Or to have my instability set in at time XYZ, you put it into this parameterization and you have your result. Similarly, for the degree of acceleration, it also scales as a linear function of the initial density difference when you have an RT configuration. On the contrary, when there is double diffusive motion, like I've said, we are not longer looking at delta rho naught, which is the initial density difference in the density difference, but then we are accounting for the dynamic density profile. This you can compute analytically if you look at my paper. And then I will show you now that if you try to correlate the mixing, the onset time and the acceleration rate with the initial density difference with this kind of setup, you are going to fail. But once we correlate with the dynamic density difference, then we'll find it. You see, the onset time versus dynamic density difference gives us this power law, like we saw in the related law case where there is no difference in diffusion rate. So this is how the density profile looks like for the ones highlighted. And if you look at the acceleration rate, if you delta rho m, that's the emphasis, not delta rho naught that was initially there. And this is just for you to appreciate what is happening. You can see it's real time, that there is a build up of minima and maxima in the density profile. It's no longer monotonic, but you have non-monotonic density profile. And then I'm telling you that once there is difference in diffusion rate, you do not control your mixing by the initial density difference, but rather you control it by the dynamic density difference. Okay, let's leave that. And you can even have more interesting results when you look at the combination of Rayleigh-Taylor modes and double diffusive modes. What does that mean? For the delta 1 is the reference case, the Rayleigh-Taylor case. But when R is less than 1, delta is greater than 1, you can see that the mixing can be even much more enhanced, happen much faster. Okay, and this is the correlation for delta equals to 1. we see scatter plot when we try to correlate with delta rho naught. You do not see a nice trend. But the moment we recalibrate with delta rho m, we find our scaling again. Same thing goes for the acceleration rate. And then I did a lot of numerical experiments, and this kind of summarizes it. We can discuss this later. And in summary of this part 1, we can see different behavior if the species, the solutes that are dissolved in our solution diffuse at different rates. If delta is less than 1, the mixing can be much more delayed. If delta is greater than 2, it can be much more faster. So the question I ask is, how fast do you want your mixing? Do you want it slower? Do you want it faster? Then you can leverage on this. Not to waste time on this simulation. I don't know why it's behaving weird, but you can see. Okay, I leave the key message because I've explained this again and again. Now, you ask, what happens if there is reaction happening? So that takes us to the full model that I was looking at. But to keep things simple, we isolate the effect of differential diffusion. We assume the species are not diffusing at a different rate. We also keep our Damkula number 1, which means chemical transport, reactive transport, and hydrodynamic transport are comparably initially. So the only thing we want to change is the buoyancy ratio. We have two, RB and RC. So an RB is measuring the density of solution B relative to solution A, and RC is measuring the density of solution C, which is the new product that is being formed, relative to solution A. So solution A is the reference solution, which is the one at the top. So what happens? In the simple case, if RB is equal to 1, 0, which is similar to the R that we saw previously, the system is stable. But if it happens that a product that is less dense is produced, as on my left-hand side, RC 0.4, the non-reactive case is stable. The only thing you see is diffusive transport at the interface, but reaction is able to break this stability and destabilize the problem. And if a much more denser product is formed, we see again that reaction is able to destabilize. But what is the difference? We can also see another control. I can influence the direction of the propagation of mixing by choosing or synthesizing products. Nothing. So depending, is this a waste product that you want to flare into the atmosphere or something that you want to transport into the subsurface? So you can leverage this already. And in the related case that I've shown you, when RB is less than 1, what do you see? What you see is that in the non-reactive case, you see diffusive propagation and then deformation because it's initially unstable. But then, because with reaction, the mixing is much more enhanced. It happens much more faster. And let me play this again. In the related case, the plumes are symmetric. That is, they tend to form symmetric fingers across the interface, but reaction breaks that symmetry. And again, if this configuration is stable, reaction is still able to destabilize the interface. So you want to wonder what is happening. It's similar to what we saw earlier. So for different parameters that we have solved, you see that these are the density profiles. In some cases, the density profiles are monotonic. So this, for example, is the situation in the region where RB is equal to 0.8 and RC 1.6, RC equals to 1.8. But in the other part, there is maximum minima developing in the density profile because something is being produced. And for different configurations, you see for Rayleigh-Taylor configuration, can you see my pointer? For Rayleigh-Taylor configuration, this is the reference case, NR, non-reactive. But when you look at reaction, uh, reaction enhances the mixing. And in the stable cases, where the stratification is initially stable, RB 1.6, in some regime, you can trigger instabilities thanks to reaction. Okay, so that kind of summarizes this. And then we quantify these nice patterns that we have seen. At what time does instability set in? We see that for the non-reactive case, most of the time, the non-reactive case NR, instability sets in when they happen to set in. When it's stable, instability will not set in. But when it's unstable and instability sets in, the instability sets in about a time more than 100 seconds. But with reaction, we can see the instability setting in below time 100. And in some cases, we can even delay it. So this is a nice way. And the places where there are no scatter points are the places where the reaction is not dense enough to trigger instability. I have told you that we can also influence the directionality of the fingers that form. So this kind of characterizes the trajectory. You can see at early time where diffusion is happening, the interface, the reaction zone where the reaction is more intense stays closer to the interface. And then for some dense products, the finger tends to rise. And then for some parameters, the fingers tend to sink. Similarly, the width of the reaction zone can expand. If there is no reaction, it usually follows a square root of time, but then you can make the reaction zone expand in time. And then for somebody that is interested in mixing, this is a kind of parameter with which we quantify the mixing that happens. It's called the scalar dissipation rate, chi. So, and it's designed this way. If you add up this equation and then you do some transformation. So it's just, the scalar dissipation rate is just measuring the variance of concentration. How far away is the concentration from the mean concentration? And if you do a volume average of this scalar dissipation rate, then you have this kind of trajectory. What does it mean? How do you know when the fluid is mixed? When the scalar dissipation rate is closer to 0, then the fluid is mixed. When it's closer to 1, it means the fluid are segregated, still unmixed. And with reaction, we can see that it approaches this red dot, RC 4.0. With reaction, the mixing closes faster for some parameters than for that parameter. Of course, I have different plots, but I cannot show the results in this talk. And then from a chemist perspective, we want to measure, okay, we know that something is being synthesized at the interface. How can we quantify the yield? I remind you, what is being formed, depending on application, may be a useful product or something that is not useful, that is harmful, that you want to suppress its formation. And we see that when the stratification is initially unstable, RT unstable, the product yield is much more enhanced. You form much more new products. And when the stratification is initially stable and reaction is happening at the interface, you form some product, but it's not as intense. So depending on application, you can already choose your stratification to decide what you want to do to end up in some regime. And the key message is that compared to non-reactive cases, reaction enhances faster onset of instabilities and intense mixing. Unstable reactive mixing is more efficient in product yield than stable reactive mixing. And reactive mixing you can modulate it by tuning the dynamic density jump that is triggered by reaction. And as a general message or conclusion, there is the initial density that the fluid feels, but then there is a dynamic density difference that the fluid feels because either the species diffuse differently, or there is active reaction happening. It's usually useful to account for this dynamic density difference to be able to make prediction about what happens. And then you can use reaction selectively to trigger or to suppress convective mixing and influence reaction yield. Okay, I think I'm going to stop here and then allow people to ask questions.
Okay, thank you very much for your wonderful presentation. In fact, I want to thank you, Dr. Johnson, for your wonderful presentation. And I really enjoyed it. But one thing I must point out to our participants is that you will notice that in this very talk, you saw a lot of graph, you saw a lot of movies, you saw a lot of what they call it, illustration that he gave. Yes, this is a right point where numerical analysis can actually come into this work. Like I told you from the beginning of this year, that I want us and as numerical analysts to begin to think of ways we can apply numerical analysis in what they call it in applied maths. We should not just stick to just developing schemes or developing methods, but to be able to help us understand some very complex systems. And this is what I am talking about. And I'm particularly, it's particularly in my own vision to transform the way, our young researchers in numerical analysis think. And for us to be able to see how we can, fit into these fields and there are so many problems that we can really understudy in fluid dynamics, in mathematical biology, in reaction and diffusion systems. And these are ways in which numerical analysts can actually come in to begin to see how they can develop their schemes and apply them to complex systems and real problems. And in this spirit, I would now welcome questions from the audience. Any question from the audience? Questions from the audience, please. Any question from the audience?
Yeah, let me ask a little question.
Yes,
Hello?
please come. My friend, Prof.
Oh, okay.
Prof. Kinedu, are you there?
Well done, Julius.
Yes,
I'm here. Yes.
Please ask your question.
Yeah. Dr. Johnson, thank you very much for your presentation. It was very, very nice. Though I didn't start from the beginning, so I don't know how you started, but I just met where you started showing the equations. I loved it because I like to see Navier-Stokes equations. So, but the discussions, I didn't hear where you mentioned how you solved the equations, the method you use or the platform framework which you use to solve the equations, or even the verification of your solution, to be sure that what you solved is actually the solution, or what you obtained is actually the solution of the problem, and not some other solution or something else that you're using to do the simulation you presented. Yeah.
Thanks a lot for that interesting question. I was expecting it. So for the numerical scheme that was used in this problem, I didn't make slides to carry you along, but I can explain and I hope you follow. So the numerical scheme that was used is what is called the spectral element method. And it's similar to the finite element method. So that's the numerical scheme. And the difference between finite elements method and spectral elements method is that you can do H refinement and polynomial refinement. And how does it work? We have a system of partial differential equations, so which is technically referred to as the strong form of the equations. And then we transform it to the weak form, or what is called through the Galerkin variational approach. So you put some test function in some Sobolev space to put this in weak form. And once you have put it in your weak form, then you choose your polynomial basis solution, the polynomial basis solution. So for this spectral elements method, it uses the Lagrange legend polynomial approach. So you have collocation points on your domain. So this you determine by solving some polynomial equations. So for example, in this problem, I've used a polynomial order of 7 for the Lagrange equation. So you find your collocation points are defined as the root of some collocation points, and then you do transformation from a reference frame, which is usually from -1 to 1. So you do a linear, what do you call it? A linear transformation from a reference frame to your physical frame. For example, in my system, X is from 0 to 400 along X dimension. Y is from -200 to 200. So these are discretized into elements like square basics. So each of the edges of these square bases on this domain, let's say along X, I have like a 500 box 6, along Y, I have 500 box 6. So these are solved as collocation points, and then I solve my system on these collocation points as roots of legend polynomial, and then I transform back to the physical space. So that's how I can explain it, but I think there are references that probably explains this better.
Any other question? Any other question?
Okay. Can you hear me? The moderator, can you hear me?
Please speak up, sir.
Yes. Can you hear me?
No, it's difficult to hear you, sir.
Hello.
Oh.
Yes,
Okay.
better.
Are you able to hear me now?
No, it's gone down again.
I can.
Can you speak up, please?
Yes, Dr. John, can you hear me?
We can hear, but it's not loud enough, sir. Please, could you try to speak louder?
Okay, so thank you for the presentation. I have actually, of course, I joined later, and for your information, I am attending from Malawi, and I am an individual from biomedical engineering. So by the look at the model itself and the numerical scheme that has been used, I think it has potential in analyzing what we call drug delivery systems. So, of course, I just want to understand what significance or how best can we employ the same thing in studying biological system, whereby, for example, someone injects there is a particular drug that has been injected in the blood. And in that case, it means we are going to have two mixing medium. Say in this case, we have the fluid that we have injected, and then we have the blood itself. So I just wanted to understand how one can use the very same qualitative analysis that have been there to explain the situation of both the diffusion and mixing that usually take place in those biological systems. On the other hand, I would like to know, of course, there is this issue of defining pollution in water bodies. So in my case, I'm interested in looking at the water body, and then we have either a chemical agent introduced in the water body. Then we can look at the very same system applied. So I would like Doc to just provide some preliminary detail on how best can we apply the very same methods that have been defined there to describe these two systems. Thank you.
Hello, doctor. Can you hear me?
Yes, I can hear you.
Okay. So, if I understand your question well, so you are looking at how the framework that was presented can be adapted to system where you are injecting something into the blood, and then in environmental study, is this your question?
Yes, exactly.
So, again, the system can be applied to different framework, and in fact, it's applicable to what you just described. You know, in a PhD, you cannot solve all the problems that there are in the world, so you have to limit yourself to some sets of problems. And what we have looked at, so that you understand what I'm saying, but what we have looked at as two solutions that are miscible. We can similarly use this system to look at two solutions that are not miscible. Like if you put petrol or you put honey or oil that are viscous, it's hard for them to mix compared to when you pour water into sugar solution. But this kind of framework can describe that too. It can as well describe the injection of something into the blood, like you rightly described, and also maybe the transport of effluent, waste into the ocean. But then it's the physics that changes. We can still use the same mathematical approach. So maybe in my model, we have looked at differential diffusion. So if there is transport of some particles, for example, we have to have an additional equation that accounts for this transport of solvents. And if you are looking at injection into the blood, for example, probably your domain will be different from mine. The boundary conditions that you look and probably the initial condition will be different from what I looked at. So I think to any system you can think, you can extend this framework to it and solve it with the same numerical scheme that I have used. I hope that answered your question.
Yes, thank you, Doctor. I've actually gotten it.
Hello.
Yeah, can we take a final question?
Okay.
Mr. Michael, do you have a question to ask? Mr. Michael, Oni?
Yes, I do have a question. Thank you.
Please go ahead.
My name is Dr. Michael. I actually came quite late too because I saw the link very late anyway. Thank you for the presentation. For the few parts I was able to hear you present. A dear doctor gave a comment the other time about the validation and justification of your numerical scheme. And also, thank you for using the spectral element method. So, generally, the numerical method is how will I put it? Is very wide at times. So, which means that we cannot really trust the solution if there are no benchmarking, one. stability 2, and convergence 3. So I think, although you didn't answer that part, and I feel going forward, maybe not here now, is one of the key most important parts when a numerical scheme is used. Otherwise, anything could be the solution. Anything could be claimed as the solution. But what are the backings to show thoroughly that these solutions actually collapse, probably to real-life benchmarking, or using a different approach, they converge to the same answers? Thank you.
Hello, Dr. Oni. Thanks for the wonderful question. It was not my intention to avoid the question on the what's the word now? On the numerics and validation of the numerics. I know this is important to mathematicians. We're always asking about convergence of the solution, the consistency of the numerical scheme. I quite agree with you, but a little background before I go to the validation. The spectral elements, by definition, when you're solving a numerical scheme, there is a numerical solution, there is an analytic solution, and then what you are trying to do is you are trying to find the difference between the analytic solution and the numerical solution and see how fast this difference approaches zero. This is about convergence. So the spectral element method is known to converge exponentially fast. So that means the error, the residual between the analytic and numerical method decays exponentially. So this is already good for this kind of class of problem. That is an intrinsic property of their scheme. So, but as to this work, how did I validate the numerical scheme? First, I reproduced known results. The Taylor problem, for example, is not a new problem. It was first studied around 1850 something, and Taylor came to the picture around 1950. So it's an old problem. So there are well-documented solutions for this problem. So I ran simulations to see that I reproduce what is already known in the literature. So that is one. Number two is what you call convergence mesh refinement test. Before I settled for the discretization that I chose, I did incremental discretization, and then I checked the current discretization with the next discretization with the next, maybe like 5, and see how far away the physics is changing. Do you get what I'm saying? So if I have elements 2000 in my system, and previously I used elements 1800 in my system, and I check the two simulations, I see that the physics are the same, the onset time are the same, the patterns that I see are the same. Of course, the 1200 is more expensive, so I can settle for what is closer. So that's one way that I test it. And then for the convergence too, you also have to choose your time stepping. Do you want to advect your solution every 0.01 seconds or every 0.00? Well, I tried all of these, and I chose the convenient one that is closer to the physics. I tried 0.0001, then I tried 00. So I chose the one that is not time consuming and that at the same time keeps the physics as 110. So these are the many things that I did to validate the numerical scheme. And I hope that answers your question.
Yes, thank you very much, Doc. Yeah.
Okay, at this point, we must go now. So I want to say a very big thank you to everybody that came. I don't know, maybe I should quickly ask. Okay, Yeah. Okay. So we want to thank everybody for coming for this seminar, and we appreciate your presence in this seminar. And I want to wish you well in your research, and to also appreciate the people that are joining us for the very first time. We normally meet every third Wednesdays of every month. In April, we'll be hosting Professor Vu Tailuan from Texas Tech University. And in the coming days, I will send you his what they call it, his talk. In May, we'll be having Dr. Victor Dansak from Sorbonne University. And in June, we'll be having Professor Yulong Su or so from what was this called? Osu, from Osu, Ohio State University in the USA. Okay, so I want to say thank you. And what time every second is it's on every third Wednesdays of every month, by 4 p.m. West African time. 4 p.m. West African time. Thank you for coming, and bye-bye to everybody. Thank you.
Thank you very much for the
Bye-bye.
opportunity to